Module 1.5, Rational Functions. Holes in vertical asymptotes. Places in the domain of a function that are skipped or do not exist. If there is a common factor in the numerator and denominator, then there is simply a hole in the domain. Otherwise, disruption, which is the place where the function does not exist, is a vertical asymptote. Let's take a look at a few examples of these. Let's take a look at the rational function y is equal to x squared minus 1 over x plus 1. If we factor the top, because it is a difference of two perfect squares, we're going to get x plus 1, x minus 1 over x plus 1. And we know from division that we can cancel these two things. So notice that there is a common factor. If we let this common factor be equal to 0, we realize that at x equals -1, we have a hole. And that's because it is a common factor. It is common in the numerator and the denominator. So if we look at this function, it's going to have a hole at x equals -1, but the rest of the time it acts like a normal line. In this example, y equals 1 over x, we're going to get a good example of a vertical asymptote. Notice that x cannot be equal to 0 because that would cause the denominator to be equal to 0. And also notice that x is not a common factor in the numerator. So therefore, we're dealing with a vertical asymptote. So what we have is an imaginary line runs at x equals 0, where this function stays away from that particular line. So notice it never hits that, but keeps and stays away from it. This is a good example, a good simple example of a vertical asymptote. Let's look at a good example of a function, in a rational function, which has both a hole and an asymptote. So if we do our factoring on this problem, we realize that in the bottom we can take out an x, and that would leave us with x minus 1. So notice that if we cancel those, we're going to be left with what is equivalent to y equal 1 over x. But don't forget that this was a common factor. So there's a hole at x minus 1, the factor x minus 1, or x equal 1 has a hole. And also notice that at x equals 0, we have an asymptote, a vertical asymptote. So let's see what this function looks like. Because of the end result, we notice that, again, just like our previous example, we have a vertical line running down the y-axis. We also know that this function will run like this on this side. The only difference is that on this side, at x equals 1, right there, we're going to have a hole. Let's look at another example of a function, rational function, that has an asymptote and a hole. If you look at this one, if we factor the bottom, we get x plus 4, x minus 1. And notice again, at the factor x plus 4, or x is equal to -4, we have a common factor, which is a hole. And in this factor, x minus 1, or at x equal 1, we have an asymptote. So we have a vertical asymptote here. So let's see what this function looks like. So again, we have a vertical asymptote. This time, instead of being on the y-axis, it's going down at x equal 1. We have our function that's running like this. The only difference is at x equals -4. The only difference is at x equals -4, we're going to have a hole. Horizontal asymptote. These are places that are skipped or do not exist in the function's range. So these are holes that are going up and down. If the degree of the numerator is less than the degree of the denominator, then a horizontal asymptote occurs at y equals 0, or the x-axis. Let's look at an example of this one. Notice that in this function we have a horizontal asymptote. Now, one thing we need to know about horizontal asymptotes, not necessarily everywhere in the range is it covered. Notice that this function does cross the asymptote. However, notice once it does, then this function starts heading closer and closer to that line without ever touching it as it goes to infinity. The same for negative infinity. Notice it crossed at 0, 0, but now it's going to start heading closer and closer to that line, that horizontal asymptote, without ever touching. Next, let's look at our second example of a horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator. Let's take a look at this example. In the case where the exponent of the numerator is the same as the exponent of the denominator, then we simply take the coefficients, which is 4 over 2. We just simply take these two coefficients, and so we're going to realize that there is a horizontal asymptote at y equal 2. So if we look, and if we graph this function, what you're going to realize is this function heads toward negative infinity. It's going to get closer and closer to that line without ever touching it, and going positive infinity, the same thing occurs. So there is a horizontal asymptote at y equal 2. And the last example we're going to look at, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Let's take a look at a function like this one. Let's take y is equal to 4x cubed over 2x squared plus 1. And let's take a look at this function. Notice that in this function, since the degree of the numerator is actually greater than the degree of the denominator, there will be no horizontal asymptote. And our function is going to look like this, where it's going to head all the way to infinity on the right and all the way to negative infinity on the left.